I'll start. I guess I had a choice of talking about quest for life on Mars or weather in the solar system. So I'm going to speak on weather in the solar system, and I'm going to try to do it a little bit differently. This has come up as a topic of curiosity several times, and I'm going to begin by talking simply about what is weather. I think this is a offshoot from a confusion that people have often between weather and climate. And so this is the dictionary definition. The Webster's New Collegiate Dictionary states that weather is a state of atmosphere with respect to heat or cold, wetness or dryness, calm or storm, clearness or cloudiness. This is the straight dictionary definition. GLOBE, which is a current project that is international. GLOBE stands for Global Learning and Observations to Benefit the Environment, and NASA manages that program, uses a slightly more colloquial definition of weather. By weather, we mean what is happening in the atmosphere today, tomorrow, or even next week. And you can see two different perspectives on the same thing. The GLOBE definition has some connotation that weather is something that's observable in the atmosphere today. And there is an element of predictability. That is, we can predict what may be happening tomorrow. And that gives you a different understanding of, okay, whether it's something that's a physical phenomena that we understand because of how the atmosphere behaves. And through that behavior, or through those laws of physics, ultimately, that we can actually predict something that's going to occur in the future. Now, to the degree our forecast works depends on how well we understand weather and how well we can model it or use the equations that we have. I don't have a definition of climate here, but a working definition would be that weather over long term becomes climate. And frequently, at least the students in the middle schools or high school have difficulty with that concept. Now, weather is not peculiar to just our own atmosphere. And I already gave away a part of my story in that to have weather, you have to have an atmosphere. Now, here I have a matrix of solar system objects beginning from Mercury and ending up with Triton. And there are some objects here that we don't think of as having atmosphere or they shouldn't have any weather. And Mercury is the classic case, closest to the planet in the upper left. We think of Mercury as a solid planet, although the purists would argue that Mercury has a very thin atmosphere. And that thin atmosphere is created from the interaction of the sun with the solid planet. There are sodium emissions that have been detected from Mercury. We don't know the source of those emissions yet, or the cause of those emissions. But it's believed that the solar wind impinging on the solid planet surface creates some emissions back. And we have seen the same phenomena even on the moon to some degree. And if you recall, a few years back, one of the lunar spacecraft, the Clementine spacecraft, was deliberately crashed into the lunar polar region to see if any water vapor came out of the impact energy. And observatories around the Earth were supposed to be observing if there were any emissions or any water vapor absorption signatures in the glow around the moon that could have been caused by the crash of this spacecraft into the surface. Unfortunately, it happened to be full moon. That's the only time they could crash the spacecraft. And because of the full moon nature, basically nobody was able to observe something because the moon was so bright that if there was any signature from any ephemeral atmosphere, it was totally lost. Next, we have Venus, a planet that has been considered as Earth's twin. Although once you look at Venus very closely, it is far from our twin. It's a planet whose atmosphere has gone awry. It's a planet with about 90 bars atmospheric pressure, completely shrouded in clouds, 100%. The details that we see in the picture are visible, or we can discern them. They're not really visible because this picture was taken in ultraviolet light and it is artificially colored. If you look at Venus through ordinary, just with our own eyes, through a telescope, basically there is no detail that you can see. It just appears as a off-white object, just a bright white ball. There's absolutely no detail on Venus. It's only in the ultraviolet that we see some clouds, we see some forms. And the question of how those ultraviolet contrasts appear is still a mystery, despite having gone to Venus at least 20 times with spacecraft, orbiting spacecraft, as well as entry probes. We still don't have an answer as to what is the ultraviolet absorber on Venus. Venus has a very hot surface. It's as hot as 750 degrees at the surface of Venus. Pressure is about 90 times that of the Earth's, about 90 bars. But the interesting thing is that if you go up to about 50 kilometers high above the surface, then you can compare the thermal structure of the Earth with that of Venus, and they're almost identical, with one exception. We have a stratosphere and Venus does not. Our stratosphere comes from ozone, which we'll come to later on, and that's a UV absorber. Ozone absorbs ultraviolet light, ultraviolet energy from the sun, and that's what heats up that part of the atmosphere. And these are some things that shape how a planet behaves or what happens on that planet. And I don't need to tell you, because I'm sure you are already aware, origin of life has a lot to do with the development of the ozone layer on the Earth. Without that ozone layer, we wouldn't be walking around on the surface today. The creatures would never have been able to crawl out of the ocean because it was only the water that protected them from the ozone. Next is Earth, and the colors are of course not completely natural, but they are indicative of how we want to think of them, as Earth is frequently called the blue planet. It used to be called the Goldilocks planet. Why? Because for a long time we thought that Venus was too hot, Mars was too cold, and Earth was just the right temperature for us. Unfortunately, that is no longer the case for life. It was called the Goldilocks planet because of the habitability issue. Habitability used to be defined in terms of, are we comfortable? Can life exist in a wide range of temperatures? And if you had asked any biologist or any astronomer or any other person, they would have said that life could not exist in extreme environments. What we have found out just in the last 2 or 3 decades is that we can find life in the frozen tundra of Antarctica at close to freezing point, and we have life where the temperature is higher than boiling point of water, 112 degrees centigrade at the bottom of the ocean near the volcanic vents, or what are called these smokers. There are these giant tube worms, and I'm sure you have seen National Geographic or NOAA programs that describe those tube worms. So this is something interesting. I think this has changed our perspective of where life can survive and what the habitability zone is. And to some degree, it has also caused us to pause and think about other aspects of weather and climate that we'll get into. Earth is not covered its surface is mostly covered with clouds, only to the extent of about 50%. If you look at the Earth from space, on any given day, the cloudiness is about 50%, give or take maybe 5%. It doesn't change much. There is a small seasonal change. However, that condition appears to be changing if you look at what kinds of clouds we have on the Earth. If you talk to the shuttle astronauts, especially the older ones, they will tell you that every time they go up, the Earth is getting hazier and hazier. And this is an important issue, and how that affects weather and climate is something that we'll explore. Earth's surface is, of course, covered up mostly by oceans. About 70% of the Earth's surface is water, And so we have land-ocean contrast. We don't have this contrast on any other planet that we know of. Why does this matter? The heat capacity of land or soil is much different than the heat capacity of water. Water has a huge heat capacity. It acts essentially as a governor of short-term changes. Any person who has lived on the coast knows that it doesn't get very cold in the winter, neither does it get very hot in the summertime. But as soon as you move a little bit inland, then you get those extreme changes. Mars does not have that moderating capability because of lack of any water on the surface. Mike, you had a question?
Yeah, I've heard that the Earth would have a very different atmosphere if life had never arisen.
That's true, and I think the Gaia hypothesis basically came out of that life, that the entire Earth is a living organism, and we have shaped its atmosphere, and if you look at the free oxygen in the Earth's atmosphere, that is entirely due to life, biological activity.
So would the atmosphere be largely nitrogen and methane then, if there was no life ever?
Or carbon dioxide. Both Venus and carbon dioxide, both Venus and Mars are extremely rich in carbon dioxide, 97% carbon dioxide, and the rest is nitrogen. So what has happened is that the carbon dioxide on the Earth got locked up into carbonates, and it's stored in the trees and other things, rocks. And if you heat those rocks, then basically all that carbon dioxide will come out and Earth will go back to Venus and Mars-like conditions. At least that's a simplistic view. Many other things will change it. Before we get to Mars, I have Titan in my slide in the upper right. And I put Titan next to Earth for a deliberate reason, even though it's a moon of Saturn. It's the only moon that has an extensive atmosphere. Its atmosphere is actually thicker than that of the Earth's. It's 1.5 times as thick as our own atmosphere. 1.5 bar is the surface pressure. The temperature is a lot colder though. It's only 115 degrees at the surface, 115 degrees Kelvin. Titan, if you look at this picture, you'll see that the southern hemisphere is a little bit brighter than the northern hemisphere. In fact, the entire the symmetry line, or rather the break line, is slightly south of the equator. And that we had proposed almost 20 years ago, that it was a seasonal effect. That somehow Titan's seasons are tied to the way its cloud deck appears. It's completely shrouded in clouds. It's mostly nitrogen and methane. It's got methane haze layers that rise about 300 kilometers above the surface of Titan. And for some time we have had doubts as to what the surface of Titan is like. Is it really solid, or is it covered with liquid oceans? Now it turns out that very likely it does not have global oceans, but it may have smaller lakes or puddles that are some organic liquids like methane or ethane, and it has to do with the organic chemistry. But Titan is seen as an analog to the primordial Earth before life started on the Earth. Now, whether life can ever evolve on Titan, it's something that we don't know the answer to yet. But it will be explored by the Cassini spacecraft beginning in 2004, when a probe enters the atmosphere of Titan, and that's the Huygens probe. And the mother spacecraft, the Cassini spacecraft, will be orbiting Saturn's system and using Titan as a gravity assist object. And we'll learn a lot more about Titan between 2004 and 2008. And that's the Cassini mission. Next, we come to Mars in the middle row, extreme left. And that's a view of Mars. It's a color composite taken from 3 different filters by the Hubble Space Telescope. And the first thing you notice is the bright white area at the top. Those of you who have not seen Mars through a telescope yet, you'll get your opportunity very soon. Mars appears just like that through a telescope. You may not be able to see the detail until you look carefully or if you have a large telescope. But occasionally you'll see one white dot at the top, and if you're lucky, a white dot at the bottom. And for many years, people have believed that this is due to presence of ice in the polar caps of Mars. And I think if you've been reading the news from JPL lately, the Mars Odyssey spacecraft, they made a big deal about finding ice in the last just couple of weeks, ice all over, especially in the polar caps, which is believed to be water ice. It's not really a new result. We knew there was water ice. The northern polar cap was confirmed to be water ice for many, many years. And those of you who have gone to Flagstaff or old enough, although I don't see anybody really that old, way back Orson Welles had a radio show that was about invaders from Mars that created quite a scare. That's a very famous Halloween radio show. Percival Lowell was intrigued by Mars. When you look at Mars, what he saw were lots of dark streaks from one area to another, and he believed them to be canals, and he came up with an elaborate theory that these were irrigation canals to take the water from the polar caps into the other areas of Mars. We now know to be not the case. Right now, when we look at Mars, we don't find any liquid water. And there we end with the inner planets. Then we go to the gas giants. Then we have Jupiter, Saturn. Then we have, in the right column, in the wrong order, actually, this is Io, a moon of Jupiter. Then Uranus and Neptune. And finally, Pluto and Triton. This is Pluto, and this is, sorry, not Triton, Charon. It's moon. Now, if you look at Pluto and Charon, that's a double planet system, the same way that Earth and the moon are. Moon is just too large for it to be our moon. It's almost half our size, the Earth's size. And that's the same story with Pluto and Charon. That may give us some indication of how Charon may have been formed. We now do believe that moon was a part of the Earth at one point. There was a giant impact at some point. A piece of the Earth got ejected into space and it coalesced into the moon. The moon has roughly the same density as the Earth. Whether that's the case for Pluto and Charon, we still don't know yet. To come back to the giant planets, then Jupiter, Saturn, Uranus, and Neptune, you can see that of the three, only Jupiter shows lots of cloud features. Saturn shows a very magnificent ring system. Uranus shows no detail, and Neptune has got a few intriguing clouds. All of these have been explored by spacecraft before. In fact, one of my colleagues, Larry Smolsky, he had an instrument on a probe that entered the atmosphere of Jupiter that was calibrated in this building just 2 floors down. Cassini spacecraft is on its way to Saturn. And the Voyager spacecraft have explored all those giant planets in the past. The Voyager 2 especially, it went to all 4 of them. Currently, we have been observing Neptune consistently from the Earth. And we find that this dark spot, which is from here to here, 2 times the size of the Earth. And hence it was called the Great Dark Spot, because it appears dark, and it's called GDS because its similarity to the Great Red Spot on Jupiter. Now, the red spot on Jupiter was observed by Galileo, so we know it has been around for more than 350 some years. Galileo observed it in the 1610s, teens, 1620s, something like that. The Great Dark Spot on Neptune, however, has vanished. It was first seen in 1989. We first saw it in 1989 January. We were able to take images from the spacecraft until 1989 August. And when we looked at it recently, the dark spot has vanished. What created this feature? We don't know yet, and that still remains a mystery and remains a topic of investigation by looking at Neptune from Earth-based telescopes and also Hubble spacecraft. All those four planets have one thing in common. Jim?
Do we know on Jupiter what caused the red spot?
There are suggestions, but no, we have absolutely no idea as to how it got created. We do know that it's an anticyclone, in that, at least as seen from here, it occurs at about 22 degrees south latitude. It's south of the equator, and its circulation is counterclockwise. That makes it an anticyclone. But beyond that, we know very little about why it exists in the first place, how it maintains itself over time. We do know that it shrinks back and forth. It's almost like a sinusoidal oscillation with a 3 to 6 month period.
Plus it gets darker and lighter.
It gets darker and lighter.
Sometimes it's really hard to see through telescopes.
Right. So there are many changes in it. Mike?
Is this the only feature in the atmosphere of this planet that is so permanent?
To the best of our knowledge, yes. I guess the only other feature would be like the ring system of Saturn, even though that's not a permanent ring system. The Saturn's ring system will vanish in some tens or hundreds of millions of years.
Well, I guess I was really wondering if maybe there were some other similar things on Jupiter.
There are, yes, there are, right to the next of the red spot, you see these three white ovals?
Mm-hmm.
And remember in this picture they came close together?
Yeah.
Well, those three ovals, they do have names, strange names like FA, BC, and DA. The names make sense when you realize that they were basically the extremities, the east-west extremities of those ovals were simply called A, B, C, D, E, F. And then how far they moved, the labels became oval BC, FA, and DA. I don't know why they went backwards, but they did. Those ovals do come together, they spread apart, and sometimes they have been cannibalized by the other one. Those appear to change over a time scale of decades.
So they're pretty nearly.
They're big. They're about the size of the Earth.
They all spin the same.
Pretty much, yes. There are other features now that has changed names like barges,
Oh, yeah.
and we don't know what they're caused either. But Jupiter is one planet where we have seen lightning. We have seen lightning optically, and we have seen lightning in terms of its spherics or its radio signal. So we do know there is lightning. Other planets, we have not been able to detect lightning. Venus actually is an excellent candidate to show lightning, but so far all we have is a controversy.
In the June Sky and Telescope, it alluded to a discussion of a mysterious ultraviolet source in the temperate regions of Jupiter. Do they know what is causing that?
In the June issue just now?
I think it was June Sky and Telescope.
Oh, okay.
It was talking about, or was it May?
Yeah, I haven't seen the article, but I suspect it was an ultraviolet image taken, and it probably is some absorber. We don't really know what causes the colors on Jupiter yet. I mean, what is the chemistry that we know very little about Jupiter's clouds. All we know is that the atmospheric composition of those four gas giants is roughly similar, mostly hydrogen and helium. The amount of helium varies on different planets. And I think one of my next slides will go into the heat balance, and the heat balance on those planets is a little bit different. But beyond that, we can't really explain why. It's impossible to explain for some reason. Uranus and Neptune, roughly the same size, almost the same in terms of atmospheric chemistry, composition. About somewhat comparable distance away from the sun. Yes, there's a factor of a few 20 AU versus 30 astronomical units. So roughly a factor of 2 difference in solar heating. Why does Neptune show these few cloud forms, which we know do change, especially in the South Polar region? They change on a time scale of half an hour. We have seen them from the spacecraft. Yet on Uranus, absolutely nothing. Now, one difference may be that Uranus is tipped on its side, its pole. Right now, we are looking at the northern hemisphere in that picture, but right now we are seeing the other side. And most recent data does indicate that there are more clouds forming. So it has to do something with the sun.
Where are the poles pointing towards us or away from us now with Neptune? Neptune's tilted, what, 92 degrees?
No, only Uranus. No, Neptune is about
Uranus.
Uranus, yes. What we are seeing is that the spin axis of Uranus is like this. This is the spin axis. And in that picture, we saw it like this. And its orbit related to the Earth is carrying us to an orientation like that, so that we are still seeing the same orientation, but we are seeing more of the other hemisphere.
Okay.
Here, all we are seeing is basically it was pointed at you, so you're seeing only one hemisphere. The only reason I included these two satellites, Io and Triton, is that they are quite a bit different from Titan in that they have extremely thin atmospheres. They do have atmospheres that seems to be created by the activity of the sun with the surface. Triton is covered with ices, water ice to some degree, methane ice, and some of that gets evaporated through, due to an ice greenhouse effect. And Triton eventually shows these plumes that are evidence of volcanism of a different kind. Now, why it erupts like that and the winds blow in one direction, we don't know yet. But they are supersonic winds. But it's the surface pressure is like nanobars, not even microbars. So it's extremely thin. And Io has a very temporal atmosphere that comes just from the volcanism, that the sulfur that's coming out remains as vapor, and then eventually actually it gets pulled into a torus that is in the Io orbit. But the interactions there are complex. Go ahead. I'm going to get some juice here.
Okay.
Come down my throat.
The 4 Galilean moons all have synchronous rotation. Does Titan exhibit that too?
Yes, pretty much. We haven't actually been able to measure Titan's rotation directly until recently when we started measuring in near infrared. It had not been possible to get a surface echo from Titan unambiguously because you get reflections from the rings. The radio beam is not that narrow, and the directivity is very hard to focus just on Titan. So it had not been possible to measure the reflectivity from the surface. That's how the radio period of Venus was measured. Mercury's rotation rate was measured like that. Mars has been a little bit of a challenge, but Mars can also be measured, the rotation rate from the Earth. But for Titan, we had to wait until we could see the infrared images. Until that time, it was just inferred that it was in.
Hubble, right?
No. Hubble is not a very good telescope for solar system studies. The only thing it is good for is deep sky studies and maybe looking at Mars, because the amount of time required, Hubble simply can't afford.
And watching comets slamming.
Yes, but it can do a survey. I mean, when you know something is going to happen, they can point to it and donate you time. But Hubble is really used for the deep sky, the deep field type studies where you want 300 hours in a tiny portion of the sky. What I wanted to add about Io was that Jupiter has a very strong magnetic field, and the emissions that come off of Io are electrically charged. And so the movement or the behavior of those particles, the ions, is controlled not by ordinary dynamics, but really by electrodynamics. It's an electromagnetic interaction. Oops. So to have weather, first thing we need is an atmosphere. We need an energy source. And to really observe weather, we need a condensate. On Earth, it's water. On Mars, it's carbon dioxide and water. On other planets, it can be methane, ammonia, or some other compounds that we don't know. Now, dust is also an ingredient that can determine the temperature source or the temperature structure of any object, especially Mars. And I'll come to that shortly. We don't think of weather on the sun, and yet here's a dramatic picture of the sun taken in ultraviolet light. I think this is the iron emission wavelength ultraviolet. And what you see are these giant storms on the surface of the sun. There are far better movies and pictures of the sun available than even this one, and I can show you the internet resources where you can find a current picture of the sun. But sun is ultimately the ultimate gas giant. A hydrogen gas ball converting hydrogen into helium, which, as you know, produces all of its output. And when that process stops, we don't have sun no more. And that's the end phase that you'll learn about later in the week from Professor Benjamin. And at that point, issues of global warming are also moved because we won't be here by that time. But sun is a fluid object, and so it shows weather of a different kind because, once again, like the Jupiter Io system, the interactions here are not just fluid, but based on the electromagnetic interactions, because all the particles that come off the sun are electrically charged, and because they're charged, they come off at such a high velocity that they have a magnetic field associated with them, and that's what causes these loops that they're not able to exit the magnetic field, and they basically just coil around and enter the sun at some other point until a coronal mass ejection event takes place, and then the whole mass in a ball is ejected from the sun at a high speed, and takes maybe a few hours to reach the Earth. And when it reaches the Earth, we get our aurora. This is how we are able to see the sun. This is a spectrum of the sun at a very high resolution, and what you see are the Fraunhofer lines here, the dark lines. They are the signatures of the solar composition. And the important thing to remember is that everything that we have on the Earth, everything in the solar system, is found on the sun. That's why the default composition for any object is the solar composition. And then during its formative phases, something happens to that composition and the relative abundance changes. But every material, every element that we have on the Earth came from the sun. It's on the sun. For weather, what is important is the amount of energy that we receive on the Earth. And here's a comparison of the actual spectrum of the sun, which is shown in red. And it's actually a very high resolution spectrum, so it looks a little messy here. But if you expand the wavelength scale, then you'll see individual lines there. And the yellow line is an approximation of a black body at a temperature of 5780 degrees Kelvin. And as you can see, it's a fairly good fit, but there are some areas which do not quite match the actual solar spectrum.
And it's above the atmosphere?
This is at the top of the atmosphere. So this does not have any absorption or scattering components. But for the most part, for most calculations, when you need to use the solar spectrum, if you don't need to use the actual spectrum, you can approximate with the 5780 black body. And this is in terms of wave numbers. You can put the wavelength differently, and I believe at the top is the wavelength scale in microns. And this is not Okay, now I wish this slide was a little bit more readable to you. I'll read those numbers. This is an activity that you can do with the students typically. What I normally do is if you have a solar system, how do you know how warm or cold it is likely to be in any object when you don't know anything about that object? Well, the first principle in physics is that we assume things are constant. This is just an easy assumption. What does that mean? That things are in balance. Now, when it comes to planets or moons, what we think of is that they are in radiative balance. What that means is that the amount of energy it gets from the sun is equal to the amount of energy they give off through the black body emission. And if you can compute that, the incoming radiation and the outgoing radiation, then it's simple to get a feel for how warm an object can be. And there's only one number you need to know besides the solar output. So this is a good activity to do with students. Planet, here's the average distance from the sun in terms of astronomical units. And here's the critical number, the albedo or amount of incident sunlight reflected back to space. It's like a mirror. Every planet acts like a mirror. And how shiny is the mirror is the simple question. That quantity is called albedo. And when you do that, and you can work this in a high school class very easily. If S is the solar constant and A the albedo, then the amount of energy falling on any object is simply the surface area times 1 minus A multiplied by S. So the energy received is simply S times 1 minus A, and S is usually given as 1367 watts per square meter. So if you multiply that by the surface area, and it's not 4 pi, it should be 2 pi r squared, and this is emitted in the black body law, so that should equal, and this is where most high school students are not able to tell the answer right away, except maybe Lynn students, the surface area of the sphere, approximate Earth as a sphere, 4 pi r squared sigma t to the fourth. This is a balance equation. And when you solve for it, you can solve for T, which would be we call it the effective temperature or the brightness temperature of the object. And when you solve for T through this formula, then you get the effective temperature for Mercury. It comes out at 436. This is what computed. For Venus, it comes out as 231 degrees Kelvin. For Earth, look at the number, 255 degrees. The average temperature of the Earth is much warmer than that. The actual temperature is 288. This is the global average temperature. And that is the greenhouse effect. The difference between the effective temperature, the radiative equilibrium temperature, and the actual temperature. That difference is the greenhouse effect. The difference, the larger the difference, the larger the greenhouse warming. And for Venus, the actual temperature is 750 degrees Kelvin. That's more than 400 degrees warmer, 520 degrees warmer than the effective temperature. So that's the greenhouse effect caused by about 90 bars of carbon dioxide. Mike?
The reason that the effective temperature of Venus is lower than the effective temperature for the Earth is because it has a big albedo?
No. The albedo really tells how bright the clouds are. Remember, the effective temperature, even though the surface temperature, and I should have said the actual temperature at the surface. Venus at the cloud top level is cool, about 200 degrees Kelvin. But as you go deep in the atmosphere, its temperature increases. So in reality, what I'm saying is that the greenhouse effect applies only to objects within atmosphere.
Yeah.
And it's the constitution of the atmosphere that dictates how much the greenhouse warming is going to be.
I think what he's saying, though, if you go down the effective temperature, It goes from large to small, and yet for
No, it's got, and what I'm saying is that it has got nothing to do with this value. The fact that it is, I mean, if the albedo were less than 0.76, yes, this will go up. And you can plug this into the formula and see how high it will be. Effectively, what that is accounting for is the difference in the distance from Venus, from the sun, of Venus, the separation.
Well, Venus is closer to the sun.
Right. But it's also much brighter, so it reflects more light off. And that's what gives
What I
it.
meant.
Yeah. Yes, you're right. It's compensating for that. Mars, on the other hand, I think if you look at Mars, the albedo is slightly lower. And so even though it's further away, you get an effective temperature which is only about maybe 20 degrees lower than that of the Earth's. But because it has a very thin atmosphere, its surface temperature doesn't change much. But then the atmosphere is so thin that the day-night differences are quite large, and the seasonal differences are also significant. Let's see, Titan, the effective temperature is 83 degrees Kelvin, which is almost the same as for Saturn, because they're at about the same distance from the sun. They have similar albedos, but the surface temperature is 115 degrees. So Titan also has a greenhouse effect. And the same for Neptune. Excuse me. I need to take this phone call. Excuse me. Hello? Anyway, this is a table that you can sort of use. You might want to develop. Normally, what I do is just leave some slots unfilled and let them work it out. Rest of them are immaterial unless you want to go into seasons and weather or daily changes, stuff like that. It has a rotation axis, the inclination given there. And I think, let's see, roughly speaking, Earth, Mars, Saturn, Titan, and Neptune are similar because they have inclinations between about 20 and 30 degrees. So they have roughly the same kind of solar insolation over the orbital period. Then you have weird planets like Mercury, Venus, and Jupiter, which should show no seasons because the orbital inclination is very little, only about 2 to 4 degrees. So Venus poles never receive any sunlight to speak of. And yet, we know from observations that the poles of Venus at the surface are just as warm as the equator. The equator pole temperature difference may be negligible, or in the wrong direction. The poles may actually be warmer on Venus than on compared to the equator. So it gets into all sorts of different situations. And Pluto and Uranus are sort of twins in that they are tipped quite a bit. Pluto is 122 degrees and Uranus is 98 degrees. The spin axis is tipped with respect to the orbital plane.
Looking at that, Venus, the length of the day versus the year,
Right.
that actually has retrograde rotation, doesn't it? In other words,
Yes.
its day is longer than its year.
Well, that has nothing to do with, that's not what a retrograde rotation is.
Well, it's
It is
revolving
going in the
opposite.
same direction, but it's spinning backwards. And that's implied by the 177 degrees inclination tip. So it's, you take it and turn it round.
In other words,
and then
flip
it's,
it and
flip it upside down, right.
And now it's spinning opposite of the rest of the planet.
Right, but it's going in the same direction as all the other planets. It's not going backwards in orbit.
Mm-hmm.
The retrograde rotation simply means that because it is spinning backwards, the atmosphere is also spinning in that direction. So the winds go from east to west.
Okay.
On Earth we think of the westerlies. Well, Venus mostly has easterlies all over, with a slightly poleward component at the cloud top. In fact, everywhere that we can measure it. That was my PhD thesis.
But it's spinning so slowly.
Right. And that leads to many interesting effects.
Yeah, the magnetosphere.
Well, no magnetosphere because Venus has no magnetic field. But it's not due to the low rotation, it's due to the lack of magnetic field.
Due to lack of
Coriolis force. There is no Coriolis effect to speak of on Venus. So you get a slightly different effect going on that is called the cyclostrophic effect due to the the curvature of the winds blowing. Centripetal force is the balance is between the pressure gradient force and centripetal force, not Coriolis force. So we'll see. Anyway, let me go on. And oops, what's going on here? Okay, let me take this again. Excuse me.
Big magnetospheres.
Yeah, to get back to the greenhouse effect, I think frequently the question comes up, what is the greenhouse effect? And here's a Earth radiation spectrum, and that is going once again in wave numbers, which is 1 over lambda. So inverse wavelengths. If you flip that number, then you'll get the wavelength in microns, radiance, and that would be the emission spectrum for a temperature for a black body emission. And then you have the carbon dioxide and ozone windows. And the next okay, the slide is slightly out of order here, but it shows a comparison of the 3 planets. The composition, surface pressure is 100,000 millibar. 1,000 millibar is roughly 1 atmosphere. That's the unit that we commonly use. These days they use hectopascals, but basically the same quantity, force per unit area. Venus is roughly 100 times that of the Earth, and a lot more than that of Mars, which is 6 millibars. Now, Mars surface pressure actually varies between about 4 millibars and 8 millibars seasonally or annually. Mars, because of topography, also has a pressure variation, because the deeper you go in elevation, the lower you go, that is, the higher the pressure, just due to the hydrostatic law.
Mars has dust storms. Right?
Mars has dust storms, but
You have such a thin atmosphere. How can an atmosphere that thin lift up the dust?
There you go. The interesting question is that Mars seasonally goes through a cycle where the temperature can be above the freezing point for carbon dioxide. And typically what happens is that in wintertime, some of the carbon dioxide in the atmosphere freezes out. And in the summer, just the opposite happens. So the modulation is due to carbon dioxide, and we don't see that happening on the Earth, at least not yet. But we may see something different, that if the temperature starts to warm up a lot, then the outgassing from the rocks may start to increase. The Earth's pressure is so variable due to other things that we don't normally see the exchange between the atmosphere, the ocean, and the land and ocean. But once you raise the temperature a little bit, then you will see a change in the pressure, the surface pressure. And we believe that's what happened to Venus, is that as it got warmer and warmer, Venus had liquid water on its surface at some point. And we can tell that by looking at the deuterium to hydrogen ratio in the atmosphere today. Because if it was solar composition, then it should be the same as on the sun. However, you find that there's more deuterium than hydrogen in the atmosphere of Venus. And the only place where that could have come from would be from water. So that's the rationale for believing that Venus once had liquid water. And you can sort of understand it, that if the water evaporated, then basically it would improve, or it would increase the greenhouse effect. Most people think that carbon dioxide is the major greenhouse effect. It's not. It's water vapor. Most of the greenhouse effect on the Earth is due to water vapor. And yet, it's not part of the Kyoto Protocol. Nobody's talking about controlling water vapor emissions into the atmosphere. And so this gets into a different aspect, economics and just the logistics of controlling water vapor. CO2 is the most controllable component of the greenhouse gases, and that's why we talk about greenhouse.
So once the temperature rises to the point where you're putting more and more water vapor into the atmosphere, then it can run away.
Then it can run away, and that's, we believe, what happened on Venus. And are we on the same track with the Earth? And the answer so far is that it's increasing, and beyond a certain point, there may be no way to stop it.
Is there a temperature effect that will drive CO2 out of the rocks where it's been sequestered?
Yes, that's. I mean, if you, I don't know what that temperature is, but yes, that's basically the case. If you hit the rocks enough, then you will have some more outgassing.
Okay, Venus has got a very corrosive atmosphere.
Sulfuric acid, right?
What is it, sulfuric acid?
Sulfuric acid, yeah.
Do they know how that?
Volcanoes.
Pardon?
Volcanoes.
Volcanoes?
Yeah. I mean, you get sulfates on the Earth from volcanic emissions. Pinatubo, Mount St. Helens, you had the sulfate particles high up in the atmosphere, and then as soon as you get some moisture, you have sulfuric acid. Los Angeles smog is basically that.
And does that ever reach the surface, do you know?
Not on Venus, because by the time it gets to surface, it will evaporate. The thermal structure will control that, and we don't really
Do
have.
you think at one time it would have? Because that would have been another operating factor for liberating carbon dioxide from.
Possible. Now, the only thing we know is that if you look at radar data, that there is a difference in the emissivities between the mountaintops and the bottoms. What that is due to, we don't know yet. But there is a detectable radar difference between the top and the
If you take
bottom.
limestone
Yeah,
and
right.
put sulfuric acid in it.
Sure, you'll get carbon
Okay.
dioxide. Yeah, right.
You said that one of the things you needed to have in order to have weather is something that will precipitate out.
Yes, I mean using something that will not just precipitate, but cause clouds. I mean, we think of weather is one of those terms which has never been truly technically defined.
Is there a temperature and pressure at which the sulfuric acid will start to drop out of the atmosphere?
What happens is that if you cool an air mass which is a mixture of sulfuric acid and moisture, basically it's a hydrous situation. So if you lower the temperature, what happens is that the concentration of sulfuric acid goes up. Water vapor freezes out, and sulfuric acid remains as sulfuric acid. Then I don't remember what the temperature is when sulfuric acid itself will freeze. There is a temperature where it will freeze, but I don't recall what the temperature
There's
is.
a temperature where it turns into a liquid.
Well, but it's below freezing point of water. It's much lower than that.
Oh, okay,
It's not higher.
okay.
And the other things to, if you look at the composition, nitrogen 1%, 78% on Earth, and 2.5%, whereas we have very little amount of carbon dioxide. And I think the next thing to notice is that the argon is roughly the same, 1%, 1.5%, and it's an interesting question. It's an inert gas. It doesn't react with anything. It's a noble gas. If you put up krypton, it will be roughly similar. But oxygen, no oxygen, free oxygen on Venus, 21% on Venus, and only 2.5% on Mars. And these differences have to do with partly lack of life, and the other thing is further away from the sun, so the photochemistry is a little bit different on Mars. So the dissociation is not taking place as fast as it happens on the Earth. Water vapor is highly variable, almost none, because if it's in the atmosphere, then it gets mixed up with the sulfuric acid, and lots of it in the atmosphere, and variable on Mars. And this is the interesting area as to where is that water coming from. There have been suggestions that it's coming from the subsurface through periodic warming, and then because of the low pressure, it just evaporates immediately into atmosphere. Now, is that what's forming these periodic clouds on Mars? We don't know, because we haven't been monitoring clouds of Mars as regularly as we would like as atmospheric scientists. That's one of the satellites that we keep proposing, and every time it gets rejected. Beyond those basic things that we talked about, distance from the sun, the thickness of the atmosphere, the things that control weather on the planets are planet's orbit, the inclination, the rotation rate, and then ultimately the composition and the surface characteristics will influence the weather phenomena quite a bit. Surface characteristics have to do with topography, and any presence or absence of oceans, and then the heat capacity differences come into play. So basically what you can see is that physics ultimately is, or rather, the weather is really determined by the physics of the planet and all its components, the atmosphere, the surface characteristics, and of course the energy source. So this is what Venus would look like if you had ultraviolet eyesight and you were looking down on the Earth, looking down on the pole. It looks like a beautiful circumpolar vortex. The equator is at the edge of the picture, and the pole is in the middle, and it's just one giant hurricane. That's what we can surmise, and it appears to be fairly steady. This view hasn't changed over tens of years. This is from Mariner 10. Pioneer Venus, about 15 years later, looked about the same. Galileo, a few years after that, presented a similar view. So as far as we can tell, the general characteristics of the Venus atmospheric behavior, circulation, are about the same. Yes, there are some small changes, but otherwise it's stable. And that's also understandable when you find out that Venus has a very small inclination. It has no land-ocean contrast. So what will change its weather?
Are we looking down at the North Pole?
This would be actually the South Pole.
We're looking at the South Pole.
Yeah. The rotations are going in the same direction. I mean, backwards. If you laid out flat, this is what Venus would look like. Somewhat akin to Jupiter in a zone belt system, but not quite. The equatorial region shows more contrast. Then there are bands from the spiral, but it's really somewhat artificial. Coming to Earth, and I just put this in for sake of provoking some thought. This is Earth at night, in visible light. And the point I used to make with this picture, and Greg has seen this picture, is that we have no business seeing Earth at night in visible light. So we are actually changing the radiative balance of the Earth. Where at night, instead of receiving energy from the sun or from any other stars or galaxies, we are actually sending visible light out into space. So this is an emission of a different kind. So far, when we talk about radiative balance, we only talk about infrared thermal emission. This is emission of a different kind.
But that was all energy that we received
Yes, from the sun.
millions of years ago.
Right, accumulated and through fossil fuels and nuclear power plants and hydroelectric plants, we are sending that energy back into space in visible light. It's a different.
A form of fluorescence?
Yes. Bioluminescence.
Yeah, I look at that and think of, well, as an amateur astronomer, how obnoxious it is, but as an environmentalist, I think, man,
It's even worse.
Tons of coal, or
Yes.
millions of tons of coal have been burned to light up the night sky.
Right. It's getting longer than what I had anticipated, but basically this is how one can break down the Earth's energy budget, the incoming solar energy. Some of it gets reflected by the atmosphere directly. This is the molecular scattering or the Rayleigh scattering. Some by clouds and some by surface. And then in the atmosphere, some is absorbed by the atmosphere, some is absorbed by the clouds, some is conducted through the air, and roughly half this energy is absorbed by the land and ocean surface. This energy is emitted by the surface, it gets absorbed by the atmosphere, and some goes directly to space and some is blocked by the clouds. So this is what makes the Earth weather prediction issue and the climate prediction issue is somewhat complex because you have to basically be able to account for all of these components. And we know that seasonally, well, here we are in Wisconsin, our albedo changes seasonally because in wintertime sometimes we have snow cover, sometimes in springtime we don't get any rain, so our land cover is different because it's not green enough sometimes, or if it's a drought condition then it looks very different. So with all these variables, you can understand why you can't always trust the weather forecasts. We don't fully, first of all, absorb all the, understand all the interactions. And we can't observe all of these minute details of the complex connections between different elements of what makes up the weather, the atmosphere, the land, and the ocean or lake surfaces. But this is one way of at least trying to get at why our weather is the way it is. This is a plot of the Earth, and this is essentially an energy diagram or an energy budget diagram. And think of it as your household budget. The simple concept that you need to understand is that what we are showing is energy as the y-axis and latitude or latitude band from pole to pole, from south to north. The blue curve shows the amount of energy received in each latitude band. Think of it as our income. And the red line is what we are spending or sending out to space. That's the terrestrial radiation. That's the infrared emission to space. And you can see that between our poleward of about about 28 degrees north on, we are sending more heat out to space in each latitude band than receiving from the sun. So that's a deficit. I mean, here's when